Every year, 11,000 tons of enriched uranium are produced worldwide. 13 countries have uranium enrichment facilities, including Brazil, which has the seventh largest uranium reserve in the world. But do you know how uranium enrichment is done? Watch this video to see all the stages of this process, from the extraction of uranium in the mines to its enrichment. Uranium is a metallic element discovered by a German chemist in 1789. The importance of this discovery was only understood a century and a half later, in 1938, when scientists discovered that uranium atoms could be split to produce energy. In northern Saskatchewan, a province in Western Canada known for having some of the richest and largest uranium deposits in the world, 500 meters below the Earth to obtain the element. The extracted uranium is mainly used as fuel in nuclear reactors to generate electricity. This mine is the largest source of high-quality uranium in the world. The uranium ore already lies beneath a layer of water-saturated sandstone. To reach it, tungsten carbide drill bits are used. The drills bore into the rock face. These first holes are for pipes that will extract heat from the ground and eventually freeze it. The worker operates the equipment by remote control, adding a new piece of pipe to the tip of the drill every 1.5 meters to reach 130 meters into the sandstone layer. It takes up to 8 days to install just one segment of pipe, and there are 200 of them. The pipes are set up to surround the ore deposit. These freezing pipes stabilize the ground and also turn the high-pressure groundwater into ice, so it doesn't interfere with the mining. A freezing plant on the surface cools the calcium chloride brine to minus 30 degrees Celsius and distributes it through the pipes. The brine absorbs heat as it freezes the ground and is cooled again. Over the uranium deposits, they are now preparing to extract the ore. They will use this drill to bore into the ore body and make an initial small diameter hole, known as a pilot hole. The pilot hole traces the drilling path to the ore and creates an entry point for larger equipment. From an elevated position, the drill will bore vertically through the rock until it reaches a specific level below the ore body. Now they are ready for the reaming drill. The equipment pulls the reaming drill through the pilot hole, enlarging the hole in the rock. This remotely controlled system keeps the miners at a safe distance from the dangers of falling rocks and minimizes their exposure to radioactive uranium. As an additional precaution, the mine is continuously ventilated, with fresh air introduced every 20 minutes. Guided by the operator using a control lever, the machine takes the ore to the scanner. By measuring the radioactivity, the scanner determines that the uranium content is approximately 15%. In most of the ore, the content reaches about 18%, which is considered high quality. The machine dumps the ore. From a control room, the operator operates a hydraulic hammer to crush the ore into pieces. The crushed ore is sent to a mill that grinds it until it becomes a fine sand. Next, water is added and a mixture is formed that is pumped to the surface. Trucks transport the uranium mixture to a mill 80 kilometers away. They stop at a special unloading facility. The size of the vacuum system aligns with the container that surrounds the uranium tank. Once in position, a vacuum tube descends into the tank and sucks up the mixture. After washing and radiation checking, the truck leaves. The mixture enters large tanks filled with acid. The acid dissolves the uranium, but not the rest of the rock, which settles at the bottom. The acidic uranium solution flows forward, leaving the unwanted minerals behind. Using a series of chemical reactions, the uranium is further purified. Then it is heated to between 800 and 850 degrees Celsius. First, the uranium is converted into gas, so that the uranium-235 isotope, which is necessary to create a chain reaction, can be enriched. This gas is introduced into centrifuges, where centrifugal forces separate the uranium isotopes according to their mass. Uranium-235, which is slightly lighter than uranium-238, concentrates more in the center of the centrifuge, allowing it to be separated. Once separated, it is concentrated into a black powder similar to coal. The powder flows into 210-liter steel drums. Then the drums are sent to a nuclear fuel processing plant. Uranium changes from black to yellow when it is converted into uranium trioxide, an intermediate chemical form. They send the trioxide in specially designed inverted cones. When it arrives, a valve opens at the bottom and the powder flows into conveyor tubes that take it to the factory. There they dissolve the uranium trioxide powder in acid. A worker takes a sample to test density and chemistry, confirming that they are acceptable. Then they add a chemical to convert the dissolved uranium into a solid. After further processing, the trioxide becomes uranium dioxide, the form needed for nuclear fuel. By centrifuging the dioxide, particles of different sizes are mixed to obtain a more homogeneous mixture. The chemical processing also turned the uranium back into a fine black powder. With several tons of pressure, presses shape the dioxide into pellets. A rotating wheel with small protrusions guides the pellets onto a channel conveyor. A pellet the size of a peanut generates the same energy as 800 kilograms of coal or 560 kilograms of oil. The conveyor takes them to the furnace. For 24 hours, the heat removes the pores, making them shrink and increasing the density of the uranium. A robotic arm loads the pellets onto a tray and levels them. The conveyor moves the tray forward. The robot places zirconium fuel tubes into a holder. Zirconium is highly resistant to heat and corrosion, but it allows neutrons to pass freely during fission. A robotic loader pushes stacks of 30 pellets into the tubes. The pellets are placed into metal tubes, which are then assembled into fuel elements that go into the reactor core. The tubes go through an automated welder that seals the ends. After the rods are welded and the assembly is closed on both sides, a robot moves it to a scale that confirms the correct amount of uranium before use in the reactor. The amount of radioactivity emitted by these fuel rods is very low and safe for handling during preparation for shipping. This nuclear fuel contains enough uranium to power 100 homes for a year. The fuel is received at the nuclear plant, where it will be inserted into the reactor core. In the reactors, uranium acts as a detonator, serving as the initial energy source that is transformed into electricity. Each of these rods generates enough heat to produce 1 million kilowatt-hours of electricity. To come to life, they must be inserted into the core. The 480 reactor tubes can hold up to a dozen rods each, and when 5,760 rods are in place, the show begins. Nuclear fission transforms matter into energy, released as enormous amounts of heat. Some uranium atoms in these rods can become excited, and when they do, they release neutrons in all directions. The tiny neutrons pass through the zirconium walls of the rods, flying from one tube to another until they collide with another uranium atom. When that happens, the atom splits, releases energy, and more neutrons, creating a chain reaction. But if it speeds up too much, it needs to be stopped. Otherwise, what scientists call a reactor meltdown occurs. The reactor is not only sealed within reinforced concrete walls 2 meters thick, it also shuts down automatically if the temperature rises or the pressure drops too quickly. The heat is used to convert water into steam, a process carefully controlled from the control room. Huge turbines in a hall 400 meters long and 20 stories high transform the steam into electricity. The turbine spins at 1,800 revolutions per minute and drives the generator. The immense wheel of the generator converts the movement into more than 750 megawatts of electricity, enough to supply 500,000 people. After about a year in the core, the rods are depleted, but they are extremely hot and radioactive. So hot that they must remain submerged in water for 10 years before they can be safely disposed of. They are placed in a pool at the plant for cooling and to let the radioactivity subside. In the depths of this 8-meter deep tank, there are more than 700,000 radioactive fuel rods. And that was today's video. Don't forget to leave a like and subscribe to the channel.